Hello everyone and welcome to another session of Würth Elektronik's webinars. I'm very happy to welcome all of you. Today's topic is component heating of power inductors in switching regulators using the IEC 62024. I'm happy also to welcome Alex Lang.
Thank you very much.
I'm very pleased to do the webinar today with you, and I will do the moderation today and Alex will do the presentation for you, and also later on he will answer all your questions, or he will try to. So regarding just some information at the first from my side, so the presentation will be about 30 minutes. After that we have scheduled some time for your questions, and so you can send us your questions with the Q&A tool. You will find that in the WebEx control panel. And then we have scheduled there also 10 to 15 minutes for all your questions. So also after the webinar, you will, in the next few days, you will get the link to the presentation from us and as well to the recording. So you have the chance to see everything again. So then I wish you a very good webinar, and I'm happy to give it over to you, Alex. Have fun.
Thank you very much. Also welcome from my side. I want to introduce myself. My name is Alexander Lang. I'm working in the product management department of the Würth Elektronik eiSos. I'm there as a tech lead and I'm responsible for the product series for the power magnetics. And I'm happy to tell you today something regarding component heating. So we are starting right away. Where is heating shown in the data sheet? I have here an example of our WE LQS, and where would we expect such a value? In the electrical properties for sure, and so we will have a closer look. So when we check this now, we can see that there are six different kinds of values, and one of these is the so-called rated current. And then if we check the test conditions of this rated current, so coming back to the initial slide, where do we want to start? We want to talk about heating and where it is shown in the data sheet, and here we have, for example, the data sheet of the WE LQS. And where do we expect a value like self-heating? Because for sure in the electrical properties. So this means if we check now these values, we can see there are 6 different ones, and one of these is called rated current. And when we then check the test conditions, we can see that this rated current is somehow linked to a self-heating of the component. In this case, it is that if the component is driven with roughly 6 amps of DC current, the self-heating is about 40 kelvins difference to the original temperature. So this is currently how it is defined in the data sheet. But why is this a big thing? Why is heating a big thing in electronics? Because heating, the colder the application is, the more efficient it is. The colder it is, the longer the lifetime of the application is. So actually rated current is the big thing. So let's go a bit deeper how things are defined, how we are doing this, and how the market is currently doing this. So going on, how is the heating linked to the losses? So this means what are we doing? We have a DC-DC converter, we are putting some power inside, our power inductor is transferring this power, and for sure by doing this some losses occur. There are 2 kinds of losses normally in a DC-DC converter, which are DC and AC losses. To make things a bit more easy, we will focus now on the DC losses and then later on the AC, but this is that at the end of the presentation. So this means there's a pretty easy function, which is I square R, which is describing how are the losses generated in a component. This formula fits quite well to ours, because the current is driven through our inductor, like we have seen in the data sheet, roughly 6 amps, and we also have some RDC, and so some losses occurs. But losses are not temperature, so how are the losses in correlation with the temperature? Let's check about this. On the left side you can see a rated current curve, how it is printed in the data sheet. And the shape of the curve is pretty similar to the equation we have on the right side. So we have a quadratic function shape of the curve, and also the equation on the right side is a quadratic function. So this means there is a direct correlation really between the losses and the temperature rise or the heating of a component. So how we are currently defining it, we have, for example, the 40K value, and in this particular case, you can see that we just draw a line, go down to the amps curve or to the amps axis, and then we will see at here, as an example, 7.3 amps, we have reached the 40 kelvins. This is how we are currently doing this in the market, or this is how we did it. And what is the current situation? So is this comparable? Let's find it out. We have here from various other data sheets from power inductors which can be found in the market, and they have specifications for rated currents like that one. That is this mentioned IRMS, 20 degrees C rise or 40 degrees C rise. Then we have things like iTemp, typically 40 degrees rise. We have also temperature rises of 50 kelvins. Then we have other specifications like 40 degrees C after 1 hour. So also the time is now included to describe a bit better how the value was defined. And also then we have 100 degrees C temperature rise after 1 hour. Then we have examples like the surface temperature is increasing by 45. So now it is described where it is measured on the part, the temp rise. We have also examples that there is a correlation between the saturation current of 30% drop and the rated current. And we have namings like approximately 40 degrees C. So again, it's an indicator of how the temp rise could be. And also just 40 degrees C temp rise. So, and last example is that there are examples which are saying check the saturation current and the rated current, and whichever value is lower, use this value as the limit. So how you can see, to name the rated current in the data sheet is already pretty difficult. So everybody is doing it the best way they think, which is okay, but what a disadvantage is, it's pretty hard to compare these values, because with such a variety of specifications, how should you know which value suits the best for my application? Because at the end, this is what I want to know. I'm choosing a part because I want to know how the self-heating will be, and then I can estimate it if this is suitable for my application I want to build up. But okay. So much for the data sheet. Let's go on. How is the heating, or where is the heating be built up? So what kind of part in the component does heat up? And this is the second part of the equation. So it's I square multiplied with the RDC. So where's the RDC coming from? In power inductors, copper wire is used. There are 3 types of copper wire, which can be round wire, flats wire, and Litz wire, but all of them are out of copper. So this means we can use the equation on the bottom left side, that the resistance is equal to the material, which is in this case copper, multiplied with the length and the area. So this means by using different kinds of wires, we can adjust our RDC. In the middle you can see a part which is using flat wire. Packing density is very high, so this means we have a high area, and that is why the RDC is going down. And on the right side you can see an example with a thin wire with a lot of turns, so this means the wire is pretty long, so this means the RDC is going up. But also, again, if you would reduce some turns, the length will go down, this means also the RDC will going down. So this means the RDC is the crucial factor where the heat is generated in our component. So where does this heat go to? It will not stay in the component, it will start to spread, because copper is a conductive material, and so the heat can also move through this conductive material. But not only. So there are several ways where the heat can be moved to. For sure, one can be the connections to the PCB. So power inductors have two connections, the start-in winding and the end-of winding. Both are soldered somehow to the PCB. And depending on the wire diameter, the heat can be moved through these contacts into the PCB and the layout. Another way is also to move the heat over the surface to the ambient. So these are the main ways where the heat is distributed. So again, it highly depends on what kind of component do we have. So we can have chip inductors like the PMCI, where we have some molding. The wire have direct contact with the material, so the material can move then the temperature to the ambient pretty good. And also we have parts like our HCFT, which have a massive copper wire inside, so the heat will be mainly moved from the wire into the PCB. And also it depends if I have an SMT or an THT component. So the variety of how the heat can be moved inside or outside of the component is there. Additionally, it's also regarding the measurement setup. So this means for sure we are focused on our component, but when we are talking about current, we have a circuit. So this means also we have a PCB, and this PCB is connection to something which is then closing the circuit. So this means by choosing a different kind of setup, so a PCB with a big copper trace or a PCB with a small copper trace, I can also influence the result of my rated current. One example is here on the left side. The very last picture is a very huge copper area, and on the other side it's a very thin one, and this is what you can see also on the right side. The black one is the PCB with pretty less copper on it, and the red one is the one with lots of copper. And this is how you can influence the rated current, even if you are measuring the same part. So this means the measurement setup also have a huge influence onto the result of your rated current value. So what is the current definition in the market for that one? We have some pretty good examples where, as mentioned, put it onto a PCB, which is out of a specific material with a specific copper thickness. So it is pretty good defined, but in 2 lines you cannot describe a complete setup pretty well. Other things we have is that where it just said it's 155 degrees C under worst case conditions, but then in the next sentence is it can be influenced by many things, so please recheck it by the end application. We have also pretty simple explanations where it just say 40K self-heating, and that's it. That's all of the definition we have here. We have here also another example where the PCB is quite well designed, also in still air, but then also it's mentioned below that for better results, please verify it in the end application. And then another result where it's mentioned it's depending on pretty many things, and so please recheck it. So overall, there's a value in the data sheet which is pretty interesting because it's mainly it's a crucial factor for the lifetime or the lifespan of my application, but the definition for this is not that specific, let's say it like this. So what are the current weak points? The test setup has an insufficient descriptions, so we know some informations but not all of them. And so this means many things can have an influence to the result of the value. And also it's very hard to put the specified values in relation to each other. So like mentioned, I want to start to build a new application. I want to have the best efficiency. I want to have the coolest application possible. So how do I choose the right part out of, let's say, 10 different parts that I just have at the end, let's say 2, maximum 3 pieces, I will then check in my end application. I don't want to check all 10 of them. Nobody has time for this. Yeah. So this means choosing or comparing the numbers based on the datasheet value is currently pretty hard. So the big question is how to improve that. And there is where I want to introduce the IEC standard 62024-2-2020. And this is what Würth Elektronik eiSos is now using and also will use in future for the classification of the rated current. So this means it's a standard where it's described in detail how to set up the measurement, what needs to be done, and then there are no more questions regarding what is the measurement setup and what is the measurement setup, full stop. And also the advantage is the standard gives 4 kinds of classifications. It means 4 kinds of different PCBs which can be used to define the rated current. And also there's already a hint for which kind or which classification should be used for which kind of product. So it means class A should be used for products which are normally used for single layer PCBs. Class B is then for double layer PCBs, class C for multi-layer PCBs, and class D is for automotive applications and also for high current power supplies. An example of them you can see on the right side. So this means the PCB is defined, everything is mentioned in there to have a proper setup which can be pretty easy understand by everyone who wants to get in touch with the specification for rated currents. Würth Elektronik is using the class B, C and D. Class B is used for parts with a standard requirements profile. So this, like I said, for 2-layer PCBs. These are mainly the parts which are for a long time in our portfolio. Class C is used for our high power density parts. So this means where are multi-layer PCBs normally used, normally for applications with a high packing density. That's why we defined it for that. And class D then for the high current parts, which is according our definition and our reference parts which can handle 30 or more amps. So going to the example, class B, we have here the WEPD. And this is a series which we have now for more than 20 years in our portfolio. Very reliable and very durable series. And like you can see here, the performance rated current is now mentioned here. And then also in the text below, what kind of class has been used with the reference to the IEC standard. So if anybody wants to recheck this value, he can build up the settings and then he will see that the results will be the same like in our data sheet. As the next example for the class C is the WELHMI. This is one part out of the molded component series. And like mentioned, molded components have a very high power density. So this means they can be used in PCB layout with a high packing density of components. Also mentioned here with the class and the description below. As a last example for the class D, I want to name the WEHCM, which is mainly used for server applications and telecommunication applications. So where are really high currents like 30 or more amps are driven. And in this example, the part can handle up to 60 amps with the proper definition of class D. Our target is to specify one series always with the same class. So this means example of the HCM. All HCMs should be, or our target is that all HCMs are then measured with the class D standard because then we can offer the service that in case somebody wants to use the HCM but it doesn't know which one is the best one, then everything is defined with the same class, and then it can be pretty easily checked what is the expected self-heating in the end application. Good. So performance rated current, sum up. What is it? So this means we have 2 kinds of rated currents in the data sheet. The rated current, like it is named here on the right side on the top, is how we measured it in the past. we have a so-called WE legacy PCB, which is, let's say, similar to the PCBs out of the IEC, but not identical. And that is why it can be that this value is different. And then we also have the performance rated current, where it's then mentioned here with the classification and the reference to the IEC standard. And then everything should be very transparent. If you want to have more detailed information regarding the performance rated current, you can also check the app note with the number 096. So, conclusions. Why are we using and why will we use the IEC standard in the future? Because by using this standard, we have the highest possible transparency. So we can really say, this is how we did it, and that is why we have that result. And it can be checked all over the world, and this is very convenient. And also, like mentioned, when I have now one series like PD or LHMI or whatever, and the complete series is measured with the same class, then it's very easy to compare which part is suitable for my end application. And also, there's a better appreciation for the end application at customer side. So this means when in the datasheet is mentioned a class C is used, then it can be already checked what are the copper layers will be used in the end application. Will it be smaller? Then for sure it can happen, or it will happen, that the rated current value will be also different. So this means I can know from the very beginning if this part is still okay for my application. And for sure there's a high trust in the values in the data sheet. So, but we are not done here yet. I want to announce here a new tool which will come in the Q1 in our Red Expert tool, Q1 next year, because I currently said I know now how everything is defined, but if I have a different PCB layout at my end application, I still have to estimate the final value. And that's why we will launch a new tool. And there you can then write in what will be my PCB layout in my final application. And then the rated current or the performance rated current will be updated accordingly. So this means with this tool we want to give a service that even a better estimation can be made what will be the self-heating at the end by using that component. So what else is missing? We said in the beginning that power inductors are mainly used in DC-DC converters. So we talked about DC losses, but what about the AC losses? The good thing is for AC losses we have a service since a long time, and this is again our Red Expert simulation platform. So this means we have here since years the possibilities to type in the application parameters, like it is the input voltage, output voltage, the frequency, the ripple current. So every main important information we will need to calculate the AC losses for the power components can be written in here, then it can be calculated, and then you can also get an answer for the AC losses. So conclusion. By using the standard, the values can be compared pretty easily. This is what we want to have. We want that there are numbers in the data sheet and I don't need to take care of how they have been specified. I know the class, I know the standard, and so I know everything is on the same level, so I can really easy compare these numbers. This is what I need. This is what I need to get a good start for my design. And then also by using the new PCB, by offering the new PCB layout tool, for sure we can go the next step and then see, okay, if I made my decision, I can already check are my top 3 part numbers all usable for my end application, or maybe just 2 of them. Then together with the AC losses out of the Red Expert, we can make a good bundle out of the losses. So this means we can describe the self-heating in all of its complexity. So we can provide a service from the start when a new application is being designed up to the end in the up to a statement how the heating will be in the final application. And this is how I want to end this webinar by today. Thank you very much for listening. And if there are any questions, I'm happy to answer them.
Yeah, so thank you, Alex, from my side for your presentation. Also, sorry again for the technical issues we have. You see, I have a different microphone. We have had some issues with the microphones, but I hope you all can hear us now in a good quality. So, yeah, so I would then open, as you said, the round for your questions. So you can just type in your questions with the Q&A function. You will find that in the WebEx control panel. So we also got in the meantime some questions. Alex, first question. Is the IEC standard used for all parts of Würth Elektronik?
Currently the plan is to use it for all power inductors. We are on a good way here, for sure. We have several thousand power inductors in our portfolio. So we started and we will step by step implement this performance rated current to all of the series. For sure, if other series and components want to use this standard, they are happy to do this. But like mentioned, currently the definition is for power magnetics. Yeah.
Thank you very much. So then let's go on with the next question. Why is Class A not used?
That's a good question. Class A has the issue that it is not 100% accurate, or there could be some definitions where are not 100% accurate. So for example, we have a component which can handle 3 amps. So we use the 3 amps PCB. But if we would use the 5 amps PCB, the result would be 3.2 amps. So both results would be right, but depending on what I'm doing, I don't have this one answer. I already have 2 answers again, and that is why we said, okay, we want to make a clear definition. That's why we start with B, and so there is nothing which can go wrong, and every value have its exact definition.
Okay, thank you very much for the answer. Yeah, also one hint from my side again. Yeah, we will later on upload the recording as well as to the presentation, so you will have the chance to get all of these questions, or to have a look at all the content again. And also, if we can't answer now your live question or your question live, we will later on come back to you via email. But then, not lose any more time. Next question, Alex. What rated current is mentioned in Red Expert or on the product label?
Okay. So like said, it can be that 2 rated current values are now in the data sheet. So when there is now just 1 rated current value mentioned, it is then always the performance rated current value, which is then like asked in the on the label or in the Red Expert.
Okay, thank you very much. Here's the next question. Würth power inductor or Würth Elektronik power inductors are ferrite type or metal type?
We have both types. So we have molded components like I showed in the LHMI, but we also have ferrite components like our WPD. So we have a huge variety. Like I said, we have several thousand power inductors in our portfolio, and our main materials are nickel zinc, manganese zinc, iron alloy, iron powder components. So yeah, we have pretty much everything which is standard in the market also in our portfolio.
Okay, so then we have another question from the attendee regarding the ferrite inductor. Has the ferrite inductor a lower RDC or metal?
This is pretty hard to answer. I tried to explain this in one of the slides. This depends on the buildup of the component. So this means whatever I want to have, I can adjust it with the wire. If I put more copper inside of the component and reducing by this the core material, then for sure my RDC is going down, but the overall performance of the component is also going down because there's now less material there. So to give a definite answer to this question is pretty hard. So my best answer is it depends.
Okay, Alex, thank you very much. At the moment, I can't see any other question. We got one more. So, is it wise to have a dedicated power for VCC layer to help with heating control in 4-layer PCB, purpose to 2-layer PCB?
My best answer would be here, it depends on the component. If it's an inductor which has a pretty short wire, let's say it like this, then which a layer like described, you can really help to suck out the heat out of the component, to move the heat out of the component. If you have a high inductance value with many turns, then sooner or later your plane can be as big as you want. The heat cannot be moved out of the component in a specific way, or let's say in a good way, because your limitation is the area of your wire. So this means as soon as the wire is getting too long, this will have just minor effects onto the result. This is also what we have seen by using the different classes mentioned in the IEC standard. If you have a high inductance value with low wire, there is no big difference if you use class B or class D. The difference is maybe 3 to 5%, but that's all you can get.
Okay, so now I can't see any other questions. Alex, thank you very much for your time today, for the presentation, and yeah, it was a pleasure.
Thank you too. I'm happy that I could be here today, and then have a good day. Thank you very much.
Also from my side, stay tuned. Have a good day. Bye.